Okay, let's start on time. Welcome to CppCon and welcome to this talk. This is yet another talk from the series of Back to Basics. We think we know C++, we at least think we know the basics, but sometimes we don't. So let's see what we have to say about strings and character sequences. My name is Nicolai Josuttis. You might have heard my name or might have read my name on some books because I deal with C++ for more than 30 years now, also standardizing C++. And I do C++ for a living, especially teaching and explaining all the pitfalls and traps and whatsoever and features. So this is about character types, strings, etc. So what do we have there in C++? Oh, I didn't try out my remote control. Now it works. Yes. So character types in C++. The first thing is you have a character, and the type of that is a char. And if you have started somewhere in your program, you somewhere have an H or something like that stored somewhere. If you assign that to a variable like auto C here, the type of that C is a char. That's an integral value. We store the corresponding value of that character in this value. This is different from a string literal. A literal where we store characters, 1, 0, or even more, between double quotes. In that case, we have an array. This is an array, and that array consists of all the characters of the string plus \0, the so-called null terminator at the end. So that's always the case, and that's not the fault of C++, it's the fault of C. The programming language C invented this idea of how to store characters and how to deal with characters and how to deal with strings. So if you assume, when I usually ask, what is the type of a string literal? A lot of people say it's a char pointer or const char pointer. No, it's not. That's not correct. It is an array of a couple of characters. It is stored somewhere in your program, and you can take even the address of that string to see where it is stored. It can often be used as a character pointer, and but this is a different thing. If you have a character pointer pointing to an array, we have in the pointer the address of the first character. So you see it here on the slide. When we initialize P is initialized with the value of this literal. The literal is stored somewhere in your program, has an address, it's a sequence of characters. P is the address of the first character. Even if it's automatically we store there the address. Then in C++ we have other types. So this is type string. We have classes now in C++, and that's a difference from C, that we can define user-defined types with data and behavior. And here we have std string, and a string is a full initialized holder of all necessary information about a string literal. So a sequence of characters stored and having its own lifetime, everything is stored in this string. It's a value type. It can be used like an int, for example. And then we have string view. If we have string view, then we have something special, which is it's a pointer that looks like a string, and it is in fact a pointer and a length, and that can be used in various places to have better performance than using strings. So the rest of the talk, we will talk about this in detail, about these types. So let's go through it step by step. And we have to say more than that was said about the first slide. So as I said, the type of high, the string literal high, is an array of 3 constant characters. It's stored like that. If you assign it to a pointer, which you can already do in C, you have the address. This is not, the thing on the right has a different type than the thing on the left. So we say that's my pointer. And the same happens if you assign it to auto. Auto automatically is initialized with, when it's initialized with an array, the type of the object you initialize as type auto is a corresponding pointer type. So that's a rule in general. So let's look at some source code. And let's see whether I'm right or wrong. So first of all, it's not so, sometimes not so easy to see and see really what I tell that it's correct. So here you have an example. Let's print out a string literal. Well, not the string literal itself. Let's print out its size. How many bytes are used here? And then later on, we initialize P and Q, one as a pointer, one with auto, with that string literal. And then we print out the sizes of that. So let's see what we have. We have 3 compilers here where we run this code. This is GCC, latest compiler. This is Clang. This is Microsoft Visual C++, online compilers. And you can see, yeah, the string literal has a size 29. And P and Q just have 8 because it's a pointer. That's the size of the address. Now you might say, okay, my compiler should know that the string literal is not a pointer, it's an array. And for that, I have done something here. One good way to get the information, what is something, is force an error about it. So get an error message with this thing. So let me assign hello to int. And let's see what the compilers tell me about this, which is not allowed. So let's look at GCC. Oh, that's an invalid conversion from a const char pointer to int. Oh, thank you very much. That's a const char pointer? No. GCC is wrong here. That's all. They have a mistake in the compiler. Don't trust them all the time. So you can see it when Clang says, no, we cannot initialize a variable of type int with an L value of type const char 6. So that's correct here. That's gives the correct type, and Visual C++ does the same. It says you cannot convert from a const char 6 to an int. So don't be confused just because your compiler says this is a pointer. It might be not. If it's a string literal, it's an array. When you specify such a string literal, you can use a special syntax, which is the raw string literal syntax. So here is an interesting string. The string has a character sequence. Let's have double quotes, then a backslash, then an N, and then double quotes. Because backslash and double quotes have special meanings in string literals, you have to put an escape character, the backslash, in front of the double quote and in front of the backslash. So 2 backslash represent 1 backslash as data. So there's one thing you can do in C++ since C++11. You can say, oh, I don't want that. I just want to write down the characters as they are, as the value is. And this is how you can do that. Use a capital R, quotes, open parenthesis, and then the value. And then at the end, you close with closing parenthesis and double quotes. These 2 string literals are equivalent. It's just two different ways to say, I want to store the combination of double quote backslash n and double quote in my value. This is the syntax between r double quote and the opening parenthesis. You can put a delimiter to specify the end, because the end of a raw string is closing parenthesis double quote. But what if inside your string it could happen that closing parenthesis and double quote is part of the value? For that, you can set up to 16 characters that in addition have to be used. And that should hopefully work most of the time. So this is a raw string direct. This is a backslash n. Now here we use a star between double quotes and opening parentheses, so that the closing sequence has to be closing parenthesis and then the star, the delimiter we did in front, and the double quotes. And here we say the closing sequence must be closing parenthesis, double Q, and double quotes. And you see, inside a raw string, you can even have new lines. You can split the line, raw new lines. And that will then be the value you see on the right. That's great if you have something like raw HTML string literals or LaTeX code or XML stuff, etc. Just write it as it is. Forget about escaping the double quotes, etc. Just put an R double quote, opening parenthesis at the beginning and the end, the closing stuff, and that's it. That simply works. So far, for raw strings, we come to them back a little bit later on when we talk about internationalization, which I will skip until the end of this talk. Next type we have is strings. Okay. A string is something you can initialize, or you can declare. It always has a value. The default value is it is empty. And by the way, it internally stores a \0 at least. So in case you need it as a C string, it has already the trailing null terminator prepared. So you can extend it, you can print it out, you can have the index operator. As usual, we don't check the index operator. You have to make sure that you do something correctly. So check the size if you don't know if the index is valid, or use @, like for vector, empty output. And you can convert it to a C string and pass it to a C function. So you get a pointer to the real memory inside. So you have to be careful. If you then change your internal memory of the string, your C string pointer might no longer be valid, and that is a problem. For that, you might say, well, let's reserve enough memory so that if I extend the string, it's big enough. Okay. Here's how it looks internally. Well, let's start a little bit naively about that. A string internally has two different informations. One is we have a fixed structure of information, which is how long is a string, how many characters can I store in the memory I currently have for the value, capacity it's called, and then the data pointer, that is a pointer to the memory the string holds. So here we have initialized a string with data. So that means, yeah, the string value is data. We have \0 at the end automatically. In case this is passed to a C function, we have it already. It's only for that purpose there. And then length and capacity is both 4. We have enough room for 4 characters and enough, and the current length is 4. This string will automatically internally allocate memory, which is expensive. Memory allocations are expensive, heap memory allocations. So, but we will improve this a little bit later. So, but this is a full string, It has its own value, it has its own lifetime. All necessary information for this object are together, are combined, are one from the outside, one black box thing. If you copy it, you get a copy of the whole string. That's it. So if you modify the source, the copy is not involved because the copy has its own value, which means the copy has to allocate memory again. We can print it out, we can compare. You know, comparison in a string is not trivial. Comparison of two strings is, let me first check whether the length is the same. If not, we know they are not equal. But if they are equal, then let's start a loop and compare character by character until we are either at the end of all the characters or we found a difference. When we found a difference, we know it's not equal. That's how the comparison operators implemented for strings. The interesting thing is if you allocate more characters, you have memory reserved for 4 characters plus \0. If that's not enough, we need more memory. And that will happen automatically. The string will allocate new memory. Here it is. Free the old memory, and in case you don't get a new value, you just, for example, append a character. The old characters are copied to the new memory. That's all done internally in the string. But this assignment can therefore become a little bit expensive because we allocate new memory and we free existing memory. Because both allocating memory and freeing memory is expensive, if we then later on assign a shorter value, we don't remove that memory and go back to the old size. We say, oh, we have enough memory still. Let's store here, for example, data is now we use of this memory, we use only the first 4 characters plus \0. So we still have room for 18 characters, but only 4 of them are used. So in case we later on assign a longer value again, we have enough memory until it's too long, and then we have to allocate memory. When this was standardized and then implemented, or it was first implemented and then standardized, we had some concerns. Because it meant that each and every time we create a string, we have to allocate memory on the heap, and that's expensive. So implementations try to deal with different ways of optimization here internally. The optimization that's now used everywhere is called the short string optimization or small string optimization, SSO, whatever the first S stands for. How does it work? The basic idea is that in practice, a surprising amount of strings are pretty short. So think about your name, think about Denver, think about zip codes, think about customer IDs. A surprising number of times, something like 8, 10, 20 characters are enough. So wouldn't it be useful then to reserve memory for a few characters and only allocate memory in case that's not enough? And that's exactly the approach. The strings internally allocate memory for some amount of characters. So for example, the value might be 15 because it's pretty often useful to allocate 16 bytes of memory, but one is for \0, so 15 is left. So that would be the content of the string, and please note that this string no longer needs heap memory, which makes it very fast. Copying is also no longer allocating heap memory, it's just copying 32 bytes or whatever the sum size, so the 16 bytes plus the 2 informations length and capacity are. Still different strings, you can print it out. And now, let's assign a long value. And that long value is more than 15 characters. We only have room for 15 characters. Oh, damn. Now we need memory. So the way this is handled is now the string allocates memory and stores a new value there. Again, if this is a plus equals, it might copy all data from the existing internal memory to the new memory. But the string has to know where the new value is stored. So we need an additional attribute. The attribute is, where can I find the value? On the other hand, we no longer need the old memory for storing the value. So that value, that memory is now reused for a different purpose. You see, the same memory, the same 16 bytes are now used to store the address of the value of the string. That way, we don't need even more size just for an additional pointer. That's more or less how strings are implemented today in all the different compilers. We don't require that in the C++ standard. It's a way that is done in practice. As we don't standardize it, we also have no requirements like it should not allocate up to 15 characters or to 50. It's up to the compilers how exactly they do this optimization. And you will see in a moment that they do it differently. Let's first finish this a little bit more. Let's add data again. Again, we have already memory assigned to this string. It's still good enough. Let's keep it because for two reasons. Freeing memory also costs time. And we might grow later on again. So let's keep it there. So we have now capacity for 31 characters. Oh, we only had here 18. So that's also another thing that compilers might do. They might say, you need space for 18 characters plus backslash 0. The 0 would be 19 bytes. Let's round it up to 32 bytes because that's the natural way memory is managed in the system. Now, interestingly, let's copy T here. Let's copy and create a copy of this string. That copy looks totally different. Because currently, we don't need memory just for historic reasons. T has memory allocated. And when we copy it, of course, we don't also do not need memory there. So the copy has a totally different layout because here the bytes in the middle or at the end of the core object, which is stored on the stack, is either a pointer to the value or it's a value. But these two strings are equal. If I compare them, if I find out, do you have the equal value, then again, we check length. And if it's equal, we check character by character. And that means, but we first have to find out that the characters for T are somewhere different than the characters for U. That's not tricky to implement, but it means there's something to do more than just simple a loop over both strings at the same location. You can see that in all these cases, the strings need memory. For example, here, we might see that all these strings need 24 bytes. It's probably a 16-bit platform, probably. We come to that in a moment, or maybe not. Because 16 bytes here, plus 4 here, plus 4 here, that's for length and capacity, that's 24 bytes. On a 64-bit platform, it's probably 32 bytes. Well, unless it's not. Let's see that. And the capacity tells you how much memory is used. Now, the interesting thing and the obvious question is, which values are the different compilers using here? I told you we don't standardize. how short string optimization is used by compilers or implemented by their libraries. So they're free to do it however they like. So let's create an empty string and print out how much memory is used. That's the first question on the stack. So you see GCC allocates 32 bytes, or not allocates, uses 32 bytes on the stack for this string. Clang uses 24 bytes only, and Visual C++ needs 32 bytes again on a 64-bit platform. These are the current numbers. Now, let's print out size and capacity. And that's also interesting. So of course, the size, that's the number of characters, the number of elements in the string is 0, but the capacity is interesting. Capacity is here 15, here 22, and here 15. So GCC and Visual C++ seems to have the policy you just saw. They allocate, or they need 32 bytes of memory. 16 are used for the character. One of them is backslash 0. So that's 15. And then they have twice 8 bytes for length and capacity, which is stored as a separate member. That seems to be the case. But Clang does something different. What the hell are they doing? So backslash 0 needs 1 byte. Then we have 22 other bytes for the characters, for the value. So only 1 byte is left to store length and capacity. Which means 1 byte means 4 bits for each of these information. Which looks like they can never store large strings with more than, 16 characters. No, they can, because they changed the layout. They changed the layout when they allocate memory. And when they allocate memory, when they don't have allocated memory, they have 1 byte used for both length and capacity. When they have allocated memory, they have more bytes used for length and capacity. That's how this is implemented. And you can see that. Let's set S to a pretty long string. And here you see the numbers. These are 51 characters. So GCC seems to allocate exactly the necessary memory for that. Clang and Visual C++ do something more. I think Visual C++ is always allocating a multiple of 16 bytes. And Clang has this internal way to see that things. I don't know exactly what the policy is. You see, short string optimization is implemented differently on different compilers, which has interesting consequences. Because it means, for example, when you switch from GCC to Clang, then your software might be faster because strings having a size between 16 and 22 no longer need heap memory. Interesting. But it could also go worse. So let's use strings where we use 2 bytes for a character. So 16-bit characters. In that case, you see, they still say, we are storing the whole string in 32 or 24 or 32 bytes. But of course, now, we have the same amount of memory available, but each character needs 2 bytes now. So what we can store now is 7 and 10 or 7 bytes without allocating memory for the string. So 7 or 10 or 7 characters, sorry, I should say. And each character has 2 bytes. And it gets worse. If each character has 4 bytes, then the short string optimization on these platforms starts to allocate memory when we have more than 3 characters inside, which is pretty often the case, I would say. So that's just that you know how the implementation of strings is done on these platforms. And if that's critical for you, you have a problem. You might not be able to use these standard string type implementations of this platform, or you could, by using your own string type, improve your performance. I don't recommend to do that. I just want to point out that you understand what's going on. Okay. Yeah, again, this is not theory, or these are numbers. There's no official documentation I found, but maybe that exists. But the link I have here, you can see the exact behavior what I had here. For example, what I have here on this slide. So here, for example, we say, yeah, size of on a Clang compiler for all the strings is 24 bytes. We are using 64-bit Clang on an Intel 68 platform, latest trunks, and yeah, and you see the numbers you just saw. Good. So far, strings. Now let's talk about string views. What are string views? String views are completely different than strings. While strings are value types, they hold everything they need to store the value, to deal with the value. String views don't do that. They are, in fact, just pointers to a character sequence, but they don't own the character sequence. The character sequence is somewhere else, which means it's a very cheap object, just a length and a data pointer. But it's a very dangerous object because the lifetime of this object uses memory which has different lifetime. And of course, it's a problem if you use the string view and then the underlying memory is used by something else. It's no longer there for what you thought it is allocated. And please note a few other things. String views might not have a \0 at the end, so don't pass that to a C string. The C string member function is therefore not available. And they might have no value, which is not possible for string. Strings always have a value, and if it's the empty string, string views might not even have the empty string, so no value at all. You can see that if you ask the data pointer, can you give me the address of the sequence, the return value might be not pointer. But they are incredibly fast. So if you have a string literal stored in your program, and you have a function foo1 that takes a string, then because foo needs a string, that string literal is converted to a string, allocating memory, at least if the short string optimization is not used, which depends on the size, and then copying all the characters, and that is then passed as a temporary object to foo. If you have a foo function foo2, which uses a string view, we don't allocate memory. So all we only have to do is we initialize the object with the length. So we have to find out how long is this literal. That's significantly faster. And there's an interesting thing. A string view can refer to a string. So here you have a string s, and we call foo2 with s, but s is a string. We expect there's a string view. There's an implicit type conversion from a string to a string view. And what that creates is what you see on the bottom. It's a string view that points into the memory of this string. Beware, if the string allocates new memory, the string view is no longer there, valid. So beware if you do things like that. Well, if you have a string view pointing to a string literal, that's fine, because string literals are available throughout the whole lifetime of a program. They are stored in memory, in the data segment. The benefit is this. Let's have a simple function that takes two strings in the traditional way, const string reference, so that they are not unnecessarily copied. We only want to read them, read access to them. So let's call and pass it with two string literals. What the compiler has to create is code that at runtime creates two strings from these two string literals. maybe allocating memory. In this case, we have pretty long strings. Well, we have 16 and 17. So on Clang, this would not allocate string memory. On GCC and Visual C++, this will allocate memory and be slower, therefore. OK, then we have the strings, and then we can deal with them in some way internally. It doesn't matter what the logic here inside is. You can implement the same function differently using string views. So print2 here is the same code, or roughly the same code, using string views. You see, by the way, string views are so cheap, it's just a pointer and a size, that we declare them by value. Because when we pass them, we just pass a pointer and a value, and that's cheap. So now you can pass the same thing because there's an implicit, you can initialize the string view from a string literal, and we save 2 memory allocations. That's good. That's worth it if we do that a lot of times. And it still works for strings because strings can be used as string views. So it allocates as before, but well, we had already allocated it. We can use the strings as they are. We just temporarily point into the memory of these strings. Please note that a string view has 2 interesting things. First of all, a string view cannot be used to modify character sequences. It's only for read access, and it does not support plus. So here on at the top, we used plus, but on the bottom, I had to do something different because of that. In this case, it's very true. Yeah. So the recommendation is, if you are keen on really good performance and you have a function taking strings, you might think about using string views. As long as in this function you have only read access, you don't pass these to C functions expecting \0 at the end. Or if you use a data pointer, double check that it's not the null pointer. So some constraints are there, but just read access is usually OK. Good. Here's the API. The API is more or less exactly what a string is. You can also say a string view is a pointer and a size with a string-like API. That's it. And yeah, only 2 things are in addition to the strings API. How good is that? So let's use it a couple of times. Let's have some vectors initializing some element that have a prefix of 1 or more characters, and then some value. And then we want to sort the elements. It works fine. We sort from begin to end. But we want to ignore the prefix while we are sorting. So how would we implement that? The naive implementation might say, let's call sort. And we have a sorting criterion which says, whenever sorting asks me, when should one string be in front of the other, according to the sort criterion, let's take the substring of this string. A and B are the 2 strings that are compared to find out about the right order. Substring will then ignore the prefix, the first n characters, which is 1 in this case. So if you do that, you see that the performance is significantly worse than before. So sort may take, for 100,000 elements, 22-something milliseconds, nanoseconds, I don't know, depending on your platform. Substring, this version, takes double, or for 1 million elements, even 3 times the amount of time. Because what happens here is substring creates a temporary additional string with value. So we copy all the characters, and if the characters have significant size, we even allocate memory for each substring, which is a nightmare whenever we compare. So here's a trick. Well, let's say, no, let's convert the string into a string view and then call substring. That is nice because what happens here is that string view is just a pointer to the memory. And for the string view, the substring function thus says, oh, a substring of 1 character, for example, adjusts the pointer 1 byte and decrements the length. No memory allocation. No characters are copied. It's just like we are using raw pointers. Yeah, we are using raw pointers. A string view is a raw pointer just with a string-like API. And see what? We have the previous performance, or even a little bit better, because we skip 1 character, which we have to compare, or more, depending on how big the prefix is. Of course, lifetime should be okay, but I mean, we temporarily create string views, and why the strings exist, why they're being sorted, that's okay. Good. Awesome. There's another thing that's important. The string implementation is so complicated that optimization is an issue. While string view is pretty forward, just a pointer and a length, optimization works great. So let's do something crazy. You don't have to understand what I do here. The important point is I take a string and do some processing with this string. I compare the first character with the last character or something like that. Yeah, I think. Whysoever. Let me call this. And once we use string view. And then let's see how the resulting code looks like. Here it is. So this is the version using full string. So we convert the stringlet, it becomes a string, and then we do the processing we need. Here it's the same, but we're using a string view instead. So now let's look at the code. We have O2, so we are optimizing. This is the code that we have for full string. So full string is pretty okay. Look at main. Oh, in total, 48 lines of assembler code. Now let's do the same here. Oh. Wow. Well, in fact, main found out that effectively nothing happens, and we just return 0 in this program. So everything was optimized away. Everything was optimized away because main could see by using string views that looking at all the things that are done here, that nothing relevant for the functionality of this program happens. While for strings, they could not see that. So here is the main function in case we're using a string. This is not optimized away. Let's see Visual C++. That's a code in Visual C++. Using string, that's a code using string view. So it's just an example, but it tells you something. It's a little bit funny. We have the short string optimization to improve the performance of strings, but sometimes it's counterproductive because the resulting complications lead to the fact that code cannot be that easily optimized away. Surprise, surprise. Good. Anyway, be careful with string view. String view is as bad as pointers, or even more. Because it's a pointer. It is a pointer. What would you not do? You would not use a pointer as a return value, for example, when it points to a local thing. But be careful, that can accidentally happen pretty easily. So this is my favorite bad example for using string view. String view initialized with the stringlet all high. You see it here. So capacity is simplified, it's not used here. Oh no, sorry, I'm wrong. That's string view, yeah, length and pointer and length. So somebody in your code base has implemented an operator string view plus string view. So you can concatenate 2 string views. And the result, of course, is a string. It's a new thing. We need memory for that. So that has to be a string. Now somebody in your project has written a very simple function template. Let's compute the sum of two elements of type t by just computing the sum and return that. Well, int plus int is int, string plus string is string, so the return type is t, of course. But if you have string view, you have a problem. Because now what happens? We passed twice this string view, twice this. And then we compute plus here, and plus calls this function, which creates a string. So that string here is returned by this plus operation. But what we return is a t. And what is t? T is a string view, which is not the string. It's a view to the string, which is a pointer to its memory. So when we pass back the return value, we destroy local objects. And that means we return a pointer to memory that was freed. Not good. So you have a runtime error. You have no idea what will happen. Everything can happen. Probably it works until you deliver it to your customer. Who has made a mistake here, by the way? So the person who implemented the application code, the person who implemented the template, the person who implemented the plus operator, or the C++ standard committee, because we have allowed implicit type conversions from string to a string view, which is in some way a violation of good principles. You should never automatically convert to a more dangerous type. But it's so nice to use. You have seen the example where we have a print function where we can pass both string and string view, and it just works. We have decided that we are fine with that. You now know the risk. Well, that's a good transition of C++. The programmer has a risk. You know the rules now. But if there's somebody who made a mistake, my personal opinion is, because I'm standard committee, I cannot be it, is, well, here's an interesting assumption made in the template. That the sum of two t's is a t, which is not always the case in reality. And especially not for string view. So you should have better double check. For example, static assert is that x plus y, is that the same as t? Or use auto. Haha, auto is your friend in templates. You don't know what you return, so you better let the compiler find out what you return, because this is generic code. Auto is your friend as return types. Okay, we can discuss forever over a beer whether I'm right to say that here's a person who made a mistake. I don't know. The important thing, you understand what's going on and what is standardized in C++. Okay, final 10 minutes, internationalization. Last topics about strings. Internationalization is a nightmare. Programming would be so nice if we would not have the reality of this world. That especially applies to internationalization. Think about length being yards and centimeters. And now we also have character sets. And we have a basic character set invented, I don't know, several years ago, 20, 50, 60 years ago, 7-bit American Standard Institute. Well, because that was a Langlois fractal of the world, using only 7 bits for each character. We had 128 characters. Well, a few of them were special, like new line. And that was enough, because we were ignoring that there are things like umlauts, the euro symbol, or Asian characters I don't even have a name for in the world. We have way more characters than 128. So the 8th bit was added. And for example, here you see NJ A umlaut. and that's a euro sign. That's a European currency sign that was invented not many years ago. And about 20 or so, or 30. And you see, for example, we now use the 8th bit to have that. But for the euro symbol, Windows and ISO decided differently what is the official value of the euro symbol. And in ISO, it's hexadecimal A4. On Windows, it's hexadecimal 80. So if you store in a character the hexadecimal value 84, it will print different characters on your platforms when you print it out. And this is still not enough. We have a lot of ISO standards. If you run this in an Irish environment, a umlaut might even mean something back, some galaxy sign or whatsoever. And then we have China and Asia and these characters from there and the Greek characters and so on, which are totally different than this. So for that, sooner or later, we need more characters, especially if we want to support all of them at once. Here we can split between Ireland and maybe Germany, but running software that might run in both countries is a problem. So we came up with new solutions saying, well, each character has 16 bits or even 32 bits, because even 16 bits is not enough for all characters in the world, especially as we now have every week 10 more characters because of emojis, yes. Good. So we are not using all 4 bytes for all the characters in the world. It's not that bad, but a lot of them are used of these values. But that means we waste a lot of memory. So the question is, how can we do best? And one approach not to waste too much memory, but still to support a lot of different characters is UTF-8. UTF-8 has the approach that major characters use only 1 byte, minor characters 2, minor characters 3, or 4. So characters use different number of bytes to be used. And yes, the decision was made from American perspective. And so A umlaut has 2 bytes, euro 3, and emojis 4 bytes, for example. At least several of them. Good. The only problem is, this is where is the 10th character? Well, except with UTF-8, we can immediately find out and jump to the 10th character. But with UTF-8, you cannot do that because you don't know how many bytes each character in front has. So you really have to pass byte by byte, character by character. Some of them are 2 bytes. So you look at certain bits of this character to decide is it 1 or 2 bytes that are valid for this character. And that's the way you jump. You iterate to the 10th character. It's not good. So for processing, UTF-8 is not great. For storing and exchanging data, UTF-8 is great. That's why it's used everywhere in IT when we exchange data or store data in databases, etc. So how good does C++ support this? Well, we support it somehow. In general, compared with other programming languages, the support is poor, very poor. Okay, so we have different types. So we have bytes, car, which then work in the first approaches. Then we have SHA-16T since C++11 for 2-byte characters, SHA-32T since C++11 for 4-byte characters. And then we have a few other interesting things. So one is UTF-8. UTF-8 support we did in the past with SHA, saying this is an array of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 30 characters representing only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 real characters. So it was an array of 30 SHA. we have changed the type for that. It's now, since C++20, this uses its own type, char8t. Please note, char8t is not the full character. It is 1 byte of this character. So, but the point is, we now have a data type that shows us, oh, if I have an array of char8t, oh, that's a UTF-8 string. I have to deal with it differently when I have to jump to the 10th element. So that is now there. But that's the best thing I can say about that. So we have a lot of support in different C++ versions. It came. Prefix U and stringlet roll switches to UTF-16 characters, so char16t arrays of char16t, capital U, 4-byte characters. Then we have the capital L, which was, we thought, a good idea, which used wchart. The only problem is wchart was not defined whether it has 2 or 4 bytes. So it's not really portable what you do there. But it's used a lot on Windows. Then we have U8. That's for UTF-8 character sequence. Please note that's an array before C++20 of char. It's now an array of char8t. And then we have U8 characters, but that's 1 byte. So it's only valid if this is a UTF-8 character that has only 1 byte. If it has multiple bytes, that's undefined, that's invalid. So if I try to write here between the single quotes the euro symbol, hopefully my compiler says that's not allowed to do. That's invalid. So strings are templates. They are templates of basic string for the character type. In fact, there are other template parameters like basic operations to deal with the characters and how memory is managed in the string. That's not important for now here. Now, we have in the C++ then a string, W string, U16 string, U32 string, for basic string of the different types. But remember, we still don't know exactly the encoding, especially if we have std string. It might be the Irish encoding or the German encoding or whatsoever, so different characters might be printed. And the same, by the way, we have for string view. How good do we support conversions? Almost nothing can be done. So we not even have I/O functions to print out a U16 string or U32 strings. Using the output operator there is not supported. And we had tried to convert from U16 string to U32 string. It was the design of that library that it came, when was it? I think C++ 11 or 14 was removed after that. It was immediately deprecated and said, oh no, that was a bad idea. And we are still working on that. Now you might say, why the hell are you not having a good solution? It's your fault. C++ is community driven. There's no company doing that. So if you want to have better support for that, do it. Come with it. Help us to do that. The remarkable thing I want to say at the end is, if I have something like U8 A umlaut, or the currency, the euro currency symbol here, that's an array of 4 characters because 3 characters for the euro symbol according to UTF-8 plus \0 at the end. And the type has changed in C++20 from this to that, which might break code when you use internationalization in your code. If you deal with that, here are some links about documents that shall help you about how to deal with that situation. I'm done. These were the basics of strings and character sequences. So, we learned a single quoted X is a different type than a double quoted X. One is a char, one is an array of 2 constant chars. Very different layouts. Often used as const char pointer, but it is not a const char pointer, the second one. String is yet another type, it's none of that. It's a different thing. It's a string holding its own value. It's a value type. It's good to use. It has a pretty okay performance until it gets really interesting. With short string optimization, which we saw, can sometimes for optimization be even counterproductive. String view is a pointer to a character sequence, fast and more convenient than raw pointers, but dangerous. You have seen that. And then we have only basic support for internationalization and UTF-8. And that's it. Thank you very much. These were just the basics of character sequences and strings. Thank you very much. If you want to see more, that's it. Not sure we have time for one or two questions. In case there are. Oh, come to the mic. Yeah.
Okay. I don't know if this turned on. If you mentioned, the community is not pushing for UTF-8 internationalization support, how would the community do that?
Well, the way we standardize it, somebody comes up with a proposal, discusses this with the other people from the standard committee. We finally say, yes, we want to have that. So we have now a couple of persons who finally came involved into this. And C++20 having its own character type for UTF-8 is the first result of that. So we have them. So if you want to join, contact me or others, and I will guide you to the right people so you can work together and help us to improve the situation.
Thank you.
Yeah. Any other question? Yeah.
First of all, thank you for the talk. I had the unfortunate experience of dealing with strings in our code base, and it pretty much hit all the pain points you mentioned.
Good. So what he's saying is I was right.
Yeah, pretty much. One of the things that you briefly touched upon was the use of string views. I was very pleased when string views made it into C++17. And I tried changing our APIs to use string views. And the biggest hurdle was interfacing with C functions and some functions that required null-terminated strings. And at every such place, I had to pretty much convert it into a string and add a null character at the end, and then use C-string to pass it to the function, which destroyed performance again. I was thinking, what's the point of doing this?
There's another thing you can do. A character sequence can be binary. Even before the trailing \0, you can have \0. So you might think about saying, my string view holds a string literal, and that string literal or that data has \0 at the end, or in the middle, where just it will end. So then you can even use string view and pass a string view to a C function, because you have ensured that \0 is there at the end as part of the size. Then the size includes \0. Right. This probably opens new problems, but it might be an idea to think about.
And just a follow-up on that, does the implicit conversion from string to string view include the \, the null terminator?
The implicit conversion from string view to string always is the official API of strings, and string is this binary, as I said.
Yeah.
So we don't care about the value of the characters we have. If a string view has a size of 7, then the size of 7 might include the \0 if it's part of the value. If you initialize a string view with the string literal, then actually I'm not sure it works. Probably not. It depends. You have to look very carefully on the constructor.
Yeah.
You have to look. You cannot use a constructor that uses a const char pointer, because that ends with \0.
Yeah.
But if you use a constructor saying, here's an address and here's a size, and the size includes the \0, then this \0 is part of the value of the string view. And that length in the string view will then include the \0 value.
Right.
Does it make sense?
Yeah.
Okay, good.
Right, thank you.
I think that's it. Have a good fun, have a good time. and see you. If you like, on tomorrow at 12, I have the book signing here, if just in case you want. Come. Thank you.